Here's a question. What are all the abelian groups of order, say, 81? Sounds like a crazy hard question, doesn't it? Like, what in the world am I asking here? What are all the abelian groups of order 81? How in the world could we possibly figure out the answer to that? Well, the fact that it's abelian helps a lot. And the fact that 81 is a power of a prime is another thing that helps a lot. These are the kinds of things to look for in chapter 11. In fact, chapter 11 is about something called the fundamental theorem of finite abelian groups. So it is all about abelian groups. If we're saying classify all non-abelian groups or any group of order 81, that's a much more difficult question. So what's the answer? Do also realize that we are talking, when we ask this kind of question, we are talking up to isomorphism. In other words, classify up to isomorphism. And we have already some knowledge of some fundamental kinds of isomorphism classes. For example, cyclic groups. Certainly Z81 is one example. But can I come up with other examples of groups of order 81 that are not isomorphic to Z81? Yes, you already know how. For example, the external direct product of Z3 with Z27 would be another example. It's not isomorphic to Z81, is it? Right? You know that, because 3 and 27 are not relatively prime. For emphasis, 27 is 3 cubed. Can you think of more examples? Sure, keep going. Z27 is not isomorphic to Z3, but with Z9. But they both have order 27. I mean, actually, also with the 3s, right? 3 to the first power. Can we keep going? Sure. The external direct product of Z3 with itself having 4 factors is yet another isomorphism class, and all those 3s could be thought of as being to the first power. Am I missing anything? Am I missing an isomorphism class? I am. Can you think of what it would be? There's one more. Think of all the ways multiplying powers of 3 give you 81, and where subscripts are not relatively prime. What's one example I'm missing? How about the external direct product of Z9 with itself? Or 9 is 3 squared. These are all the possibilities. There are 5 of them. All the possibilities. 5 of them. Now you might wonder, well, really? Is that really right? Like, for example, couldn't I also write the external direct product of Z27 with Z3? And the answer is, I mean, yes, you can write that, but it's nothing different. It's isomorphic to the external direct product of Z3 with Z27. So it's not giving you anything new if you write that. These are all the possible isomorphism classes. There's nothing special, actually, though, about the prime P. I could do the exact same kind of thing for any prime P. There's nothing special about the prime P equals 3 is what I tried to say. I could do the exact same thing for any prime P. And 4th powers. 81 is 3 to the 4th. I could think about abelian groups of order P to the 4th. And I'd also get 5 possibilities. The cyclic possibility, that possibility, working by analogy here, this one, and finally, an analogy with this one, it would be the external direct product of z p squared with itself. So there's nothing special about the prime p equals 3. Any prime would work, and you'd have 5 isomorphism classes if you're talking about groups of order p to the 4th. Why 5? It's related to what are called partitions, which is the number of ways of adding positive integers together to give you other positive integers. In this case, there are 5 ways to add positive integers together to give you the number 4, which is the power of the prime we're talking about here. And that's ultimately why there are 5 groups here. That's a key idea to look out for in the lectures and also in the reading.